Okay, so we've always gone through this process of working on number 10 together. So if we're going to do that, it just makes it much easier if we do this without a lot of sidebar conversations, because some people probably do want to listen to this content as we go along. And the quicker we get started, the quicker we get started, okay, the quicker we could possibly get done. So how many of you have even looked and read number 10, just thought, I'm not doing that? Okay?
10?
Right.
I'm working on it.
Okay? So, what this means, if we follow along, the energy used to power the Apollo lunar mission was supplied by the reaction below. For the phase of the mission, when the lunar module ascended from the surface of the moon, a total of 1,200 kilograms of N2H4 were available to react with 1,000 kilograms of dimethyl hydrazine and maybe 4,500 grams of dinitrous oxide, I think it was, and hydrazine's the other one. For this portion of the flight, which of the allocated portions was used up first? So this is a limiting reactant problem. It doesn't mean that a reaction is not going to proceed. That's not what limiting reactants means. It just means you are limited on what you can actually do. Okay? So, for instance, maybe a band won't sound as good because their main bass drummer is sick the day of a competition. Or maybe your leading scorer or quarterback is injured, or leading scorer in basketball. If they have to sit out, you are limited on what you can do. So limiting reactants works in a similar manner. It doesn't mean that you can't participate or can't move forward. You're just limited on what you can do. So as we proceed forward, how many of you still have a set way of doing this, where you have moles and you convert it to moles of your other reactant and then moles to the other reactant, see how much is required and how much you have? How many of you are still doing that process? Isn't that how we started, though? Yes. Okay. How many of you are just going straight from grams to grams, changing how it is you want to approach these? Okay. Well, this is how we'll do it, and we'll illustrate it both ways if there's time. Okay. So here is our reaction. I think isn't the equation balanced for you too? I have to do that, but we'll just do this instead. Okay, so 2N2H4, okay, plus N2H2 okay, so we know there's water that's produced and nitrogen. Okay. So if you wanted just a slight history lesson, okay? And sometimes there's phrases that we hear in history that will just always be remembered. The Hindenburg, do we know what that is or was? It was a blimp, right? It was going from Europe, I want to say England, across the Atlantic. It was going to land in what, New Jersey maybe? The theory is the coating on that Hindenburg had, let's say, got too close to some power lines. It ignited, and then that Hindenburg caught fire. Now, when you look at these blimps, wouldn't you say they're about the length of a football field, or even longer, possibly? So just picture a blimp that has the nose next to the bus barn and the tail fin maybe comes all the way to this science room here. What gas is that?
Helium or hydrogen.
Hydrogen at that time. They probably use helium now, but at that time they used hydrogen. But what had happened is once that had ignited, I think if you can see the video, one of the things you hear, what's this phrase that is all throughout history? Oh, the what? I think some of you may have heard of it. Oh, the humanity. Okay? Because that's what a radio announcer was talking about. Okay, here comes the Hindenburg. It's going to land. All of a sudden it catches fire. Oh, my gosh. Oh, the humanity when it burned up. When that hydrogen combined with the oxygen in the air, in the atmosphere, you have that spark. Who knows how many thousands of pounds of water fell out of that. Okay? So when you think about combustion reactions, that's what we're looking at here. That's why it's asking how much water probably ended up on the moon from this lunar reaction. It's hard to visualize something like that happening, but that is what exactly would take place. But you're thinking to yourself, wait a minute, there's no air in space. So where is this oxygen coming from? Well, as these gases are combusted, we see there's oxygen in here that can combine, and that's why you have it on the other side. Okay? But anyway, not that you needed or wanted to know that, but I thought that was kind of neat just to give you a little history lesson. Okay, so N2H4, there's changing that to grams, you'd have how many? That many, right? Okay, and that's N2H4. Okay, and I know these numbers are astronomically large. That's why maybe it's a good reason or a good idea that we're going over them together. So if we see this many grams, we're going to convert it to what? Okay, so 32.06 grams of N2H4 gives you a mole of N2H4. Okay, so upon doing that, you divide this 1,200,000 by 32, and you get approximately 37,499, 494.
Yeah, 420.
Okay, 429. Okay. Mole of N2H4. Okay. Then we'll move on to our next one, which is 1 million grams. And I just abbreviate this because you actually see it on your paper. Okay. Okay, so DMH is this compound here, okay? I think it's called dimethylhydrazine, and then we've got a mole of that substance. So once we divide those out, again, we get a very large answer, 16,633. Okay, are you with us so far? I mean, other than the numbers being very big, there's really nothing new here. We see something in grams. You take the atomic mass, divide it in there to give you your moles. Okay, then at the very bottom here, okay, we've got 4.5 million. Okay. And then, what is the atomic mass of N2O4? Right? For somewhere there about 68 plus, or excuse me, 64 plus 28. Okay. Okay, and then that gives us 48,000, I think.
There are three of them.
Sorry?
There are three. There's a three coefficient on
No, it's not.
Not yet.
it. Oh,
It's
Not yet. Okay. 48,900. I can't quite read it. 48,902. Yep. Okay. Now, that's not right. These numbers are signifying what?
What you have.
This is what we actually have. Probably one of the things that's maybe throwing you off is because there's 3 reactants in this problem. Okay? So you have to remember a limiting reactant, it's limiting how much of these substances that you're going to produce. Okay? So the next step is maybe what would be perhaps a little tricky. So we'll put variables in for that. We'll just say this is reactant A, this is reactant B, and this is reactant C. You could do the same thing here, A, B, and C. Okay? So if we just worked with this number here, moles of N2H4, we're going to change that to moles of what?
Water.
No.
One of the other two.
One of your other 2 reactants. Are we following along? It's just like if we would have just 2 reactants here, you convert moles of what you have into this to see how much is required, moles of this converted into moles of letter A to see how much of that is required. Okay. We following so far? Are we just nodding our heads yes? Yes.
does it matter which one you pick?
No, but make sure
No.
you use the same one for the rest of them.
Exactly.
Yeah.
Okay? So, in other words, if you changed A to B and then A to C, okay, then there is just, that will tell you how much of each substance then is actually required. Okay? All right. So let's just go ahead and change letter A, this one, into variable B, just to see how much of that is actually required. Now, when you have mole over mole, you have to refer back to your equation, correct? Okay. So, we can just go ahead and erase all of this work if we wanted to, but maybe you'd rather leave it up there. That's what's nice about having different colors, okay? Keep it or erase all of this. Okay, so if we did that, this would be a good idea. 37,429, 16,633, and then 48,902. Okay? And I understand you have decimal points on there, but when these numbers get that large, okay, chances are those decimal points are going to be irrelevant or can be neglected. Okay? So we're going to go ahead and get rid of all of these. Okay? Okay, So we're going to go from A to B to see how much of that is required. Okay? So we've got 37,429 mole of N2H4. Okay? So how do we convert moles of A to B here? Okay? Moles of what goes on the bottom? And then what would go on top if we're going from moles of this to moles of that? Okay? So therefore we've got mole of DMT. I'll write that up here. DMT. So we actually know what that means. We're not quite done with that step. Okay? If you know what we're missing, don't say anything. You are not doing yourself any favors if you're sitting there going, yes, I follow this one. Actually, I really don't. You are not helping yourself. Okay? So, if you're not following, okay, it's tough to admit that. I think sometimes that's tough to admit that we have problems. And it makes me laugh about this situation that, and I've said this before, it was in a church sermon. And I don't know if it's changed, but it used to be the number one shoplifted item. Keep an eye out for that now. The number one shoplifted item is this product. It's not that you're not that far off, but preparation H. People don't want to go through the checkout line with this preparation H because they're admitting that they've got problems. Everybody's got problems. Okay? Some people, maybe more than others, maybe others are better at dealing with them. But until you confront that problem, is it ever going to get any better? No, it's not. It might over time, but holy cow. Why don't we take care of ourselves and nip this in the butt, ha, 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 right away? Okay? Yes, we've all got problems, but until you confront them, you're just not going to get any better with it. So, if you don't understand, what are we missing in this step?
The two in front.
So you don't understand?
He wants people that are listening and paying attention to answer.
Okay. So then,
I was trying to figure out the next part.
so we need a coefficient. Where does that coefficient go? Why are you right? Okay. Because we have a 2 here. It's in front of that N2H4. So we go back to our chemical equation. There is a 2 there. So once we divide that, okay, that gives us 18,624. And then what else would you write over here? 3 letters. Say that again. Yeah. R, E, Q. This is required. We need 18,624. How much did we have?
I'm not getting it. I got 18,704.
Oh, 18,000 what?
7.
Okay. Okay. Do we still have enough?
714. Like 1.
Yes.
Okay. Well, I'm sorry. We're not 18,000.
714.
Okay.
Yes, we still have enough.
Yes, we still have plenty. Okay? So, we went from A to B. Now let's go from A to what? Let's go from A to C. Okay? So same thing. 37,429 mole of N2H4. So how do we get into moles of C now? We're going to do that same thing down here. And then what goes up top then?
moles of C.
Okay? Are we missing anything here? Okay, that too, just like we did in the prior step, belongs there. And then once you do that, 55,874. I feel pretty confident with that. What else are we going to write here? Required. Okay, this is required. Okay, we need 55,874. Okay, how much do we have?
Not enough.
Or excuse me, over here.
Not enough.
Not enough. So it's possible
But that's not.
there's still one left yet because we don't know how much of this is required. Okay, so maybe it seems a little redundant, but what you can do is go from B to A. Okay, now you might say, well, we've done that already, but you haven't done it with either of these numbers. Okay, so we'll just go from C to A. Okay, because I don't like writing this whole long thing out. Okay, so we're going to put 48,902. Oops. Okay, and that's moles of N2O4. Okay. What is our next step to get from moles of this to moles of that?
Moles of C on the bottom.
Okay, so that would be moles of N2O4, and then moles of what? N2H4. Okay, then when we calculate that out, we get 32,601 mole of N2H4. That's the answer you get, but you're not going to get it unless you fix this problem. Yes? Unless you fix this problem.
The two.
2 or 3? I heard 3. 2. Did I miss a coefficient? Oh, there's a 3. Okay. I mistakenly left that out. I didn't, but I do know we have to have a 2 down here. And N2H4. Nope, we need a 3 down there. And a 2 up top. But you still get 32,601. Okay? And then that is REQ. Now, as you're looking at this, you might be saying, holy cow. Is that our limiting reactant? No, it is not, because for N2H4, we need 32,000. We've got 37,000. Okay? For N2O4, we need 55,000. We only have 48. Then for this top one, we need 18,000, but we only have 16,000. Now you might think, well, both could be your limiting reactant. No, that's not the case. Which has a larger discrepancy? In other words, if we do this, N2O4, we put 55,874 and subtract. Then if we did the same thing here, 18,714, which one has a larger discrepancy? Which one? Letter C. So then, moving forward, this is your limiting reactant, okay? Because it's the one that would get used up first, okay? So mistakes happen. I mean, just looking at some older videos like the Saturn rocket, I mean, something had to have been miscalculated there because that was one really large explosion. So when that happens, somewhere along the line, perhaps some engineer miscalculated this. It happens, okay? But that's how you find your limiting reactant with that. It's a little shorter, but maybe it's easier to make a mistake. Or if you're maybe like someone in this second row, if you change grams of this to nitrogen, gives you a number. Grams of this to nitrogen gives you a number. Grams of this to nitrogen gives you a number. The one that is the smallest, which would be this one, would be your limiting reactant. It's a different way of solving for it. Okay. Rut row. We're good. We're good. Second row. And we're going across. Third row. Okay, a lot of this, that's good. We saw about 3 of these and some Okay, you still have some time to work on that. Or if you got, I have no idea what I'm doing, now would be a good time to ask. Yes. Yes. Otherwise, the rest of the time then, okay, then I would say the rest of the time then is your pause. Okay, for number 8, disregard the percentage there. You're changing 1,250 grams of carbon to grams of methane, which is CH4. All right. If there's nothing else, I'm going to shut this off. Going once. Going twice. And keep in mind, yes, this material is difficult. If you feel like deflated, defeated, knocked down, do this. Get up and keep moving, okay? I think I can speak for any staff member here. Turning in blank papers or not, that's not good. If you're at least turning something in, you're getting up and you're moving forward. That is our goal, to keep moving forward. Okay, we'll catch up to you next time.